Presented by Caltech.
Thanks for the invitation. It's really great to be back here at Caltech. I only get out here every couple of years now, even though it's such a short plane ride from Stanford. And of course, it's really wonderful that this program and this fund has been set up. And so I'll just share a few comments about my background and how I came to end up in Carver's lab. And what I thought was there's so many things that I learned from him, and but I'll try and focus on oh wow, this is like my favorite cough drop. So I'll try and focus on the most just one. We don't have a lot of time, but so let me just say put things in perspective. I had my first neuromorphic chip paper was published in 1989, in May of 1989, which was 30 years ago from last month. And I mentioned this to a EE Times reporter, and he put out a story. We had an interview, and he talked about how the field was and the evolution, and where I think things are going now, and that it's a really exciting time that we are in right now. And but the title, the editor picked the title for the article that AI veteran pushes for neuromorphic chips. So I guess I'm officially a veteran. But anyway, he of course asked me to make some comments about Carver and what did I learn from Carver and so forth. And to put that into perspective, I'll back up a little bit. So I was an undergrad at Hopkins in 86, 87. When I took a VLSI design class, a lot of you would know that this was using techniques that Carver pioneered and made it possible for actually students in universities and people who didn't actually own these fabs to be able to do this. And he went around, traveling around the country, evangelizing, running workshops, and so on and so forth. So I benefited from that. And this was the second half of the 80s when neural networks were hot, and everybody was getting into it. And so my first chip that I built was based on one of these abstract mathematical models of neural networks. And the reason why I was interested in that was when I got my first computer as a teenager, I was like 19 or so, and my father was in sabbatical, and he brought one of these BBC microcomputers home. And I always had a little laboratory, I used to think of it that way, where I was taking things apart and building things and so on and so forth. And it was each one of those experiments to me was a new adventure, right? But my parents called it konkaka, the noise that you make with a hammer, taking things apart. So he's doing konkaka, and I was thinking, I'm having new adventures here. So I love that name of the program because that's how it felt. And but I was too intimidated to take the computer apart, so I went to the library and I studied everything I could about computers, PC, memory, LU, logic unit, and so on and so forth, all the way down to the zeros and ones, Boolean logic, and building all the way up to be able to do these operations and so forth. And I thought that was a tremendous amount of work this poor little computer had to do. Carver described it as you basically flog the horse really hard and get him to really gallop really, really fast. And if you can get him to do that, eventually you'll get some results. And so I looked at it and I was like, I think there has to be a better way to do this. There has to be a more elegant way to do this. And but I had no idea. I didn't know anything about the brain. I hated biology. So I get to Hopkins, and this kind of milieu of this wave of neural networks hype and so forth. And I said, wow, okay, this is actually a much better way. This is much more elegant, right? And but I still had some doubts about myself because I talked to these guys. I came from Ghana. I talked to these Americans, and they're all about computers. Everybody loves computers. They love to program all this stuff. So when I met Carver, the most important thing that he taught me was you should trust your gut. Okay, like basically these doubts that I had, it's like just go with your gut. And that actually made me more of who I am, right? I basically, so that was a real gift, like to set me on a path where I really persisted and trusted that, and he encouraged me to do that. And so I wore this bright shirt here in honor of Carver, because that was one of the things that stood out about him. You know, in Africa, we wear all these bright shirts, and I come to America, and everybody's in like white and like light pastel colors. And Carver shows up, and it's this design on his shirt, and it was just like, wow, okay, who's this guy? You know, and so that made me feel really at home. My father was a professor. He made a point in showing up in every lecture with a nice, bright, dynamic shirt, because, you know, yeah, so. That was an instant point of identification. So that's the background, but just to close the loop, and so now we are in 2019, and neuromorphic chips are all the rage. There's all these hardware AI companies. Everybody's making chips now after about 10 years where we thought it wasn't going to happen. And you know, so he was right. And so I think people haven't emphasized this, that Carver is really a visionary. Okay, he's done this several times where he's looked into his crystal ball and been able to tell us what's going to happen in 20 years and 30 years and so on and so forth. So yeah, that's how how much he trusts his gut. Okay, so with that, let's do a few introductions to the speakers that are coming up. But I want to make one comment about the talks before, which were really fascinating. You know, it really kind of gives me this same feeling I had when I was here as a graduate student, this special thing about Caltech, where it's just everybody is just doing such incredible things, and they're so humble and they explain it so simply, and it's like, yeah, of course. Okay, so so anyway, but the most interesting one was the talk by the philosopher, and if you had spent any time around, I would have asked the same question that came from that side of the audience, but I've spent some time around philosophers, and I realized that, you know, what philosophers do really belongs in science, because they actually are trained as to how do you frame a question that's answerable. Okay, so they don't come up with the answers, but they come up with the questions that are answerable, and that's what you have to do in science, and that's why originally it was called natural philosophy. Okay, so yeah, so thanks for being here. With the philosophy aspect of it. Okay, so we'll press ahead. The next talk, and I know a little bit about both of these talks, so I'm really looking forward to these talks. They're in my area. So the next one by Alireza Marandi, I just give you a little bit of his background. It turns out that he got his PhD from Stanford, let me try and get the year correctly, in 2013. And so, yeah, nice to see some Stanford folks here. And his background, he's an assistant professor. Alireza Marandi is a full name. He's an assistant professor in electrical engineering and applied physics. And he's basically looking at photonic computing. And this is another area. Of course, we're at the end of Moore's law, as Carver predicted, and we have to figure out where we go from here. So these are one of the new exciting adventures that we're going on. And so with that, I'll let Alireza take the
Good afternoon, everyone. So before I start the talk, I should thank the organizers, Adam and Azita, for putting together the symposium and also the opportunity to speak here. It's really a great pleasure to be here and talk in front of this audience. And of course, it's great to be here in front of Carver and all the inspiration for many generations of scientists and engineers. So today, I'm going to talk about Ising machines, which is basically a hardware platform as an optical computer. And I'm going to talk about this platform, which is not a standard digital computer as we know it. It's targeting very specific types of problems. So before I dive into details, I should mention that some of the results that I'm going to show is a result of contributions of many people from my previous life at the University up north, with a wonderful group of students and postdocs, and also professors and collaborators from all over the world. Most importantly, Peter McMahon and Ryan Hammerly are responsible for some of the recent experimental results. And also my new group here at Caltech, which is now composed of 3 students and 2 postdocs. Some of them are already here, so they're giving me more stress than the other part of the audience. And with collaborators from all over the place. So in computer science, there is this class of problems known as NP problems. And one of the characteristics of these problems is that if you use a brute force algorithm on a standard computer, the computation time scales exponentially or faster as the size of these problems grows. And these problems are everywhere. So in biology, for instance, protein folding is known to be an NP problem. In sociology, maximizing the fluence in a social network is known to be an NP problem. And we have a large class of combinatorial optimization, and there are two examples of them in engineering that belongs to this class of NP problems. So there is a demand for thinking about a machine or a hardware platform that can maybe target these types of problems and can maybe solve them a little more efficiently than the standard computer. So we pick one of these problems, which is called the Ising problem. And the Ising problem is basically based on the Ising model in physics. So the model is that if you have a magnetic structure which is made of a bunch of magnetic domains, and each domain is either up or down magnetic spin, as you know, magnetic, and they're coupled to each other, so they interact with each other through a magnetic field, you can explain the energy of the whole system by this simple summation. The Ising problem is that if you have a magnetic structure and you want to figure out what would be the spin configuration for these domains that would give you the lowest energy for the whole system, is actually the Ising problem. So if you know the Jij, the interactions between these domains, what is the spin configuration as the ground state? So finding the ground state of the Ising Hamiltonian. So this is important from the computer science perspective because it falls into this category of so-called NP hard. So the term hard here is important because that means that this problem is a representative of the whole class of NP, meaning that you can map any NP problem to an Ising problem with polynomial time overhead. So that means that in principle, if you have a machine that can solve the Ising problem efficiently, you can think of having a machine that can solve almost all sorts of NP problems efficiently, in principle. In practice, it's a little more different. So the idea of Ising machine is that can we make a physical system which is made of a bunch of elements, and each element has this variable that can be either +1 or -1 to represent an Ising spin. And if we can connect these spins to each other, these domains to each other arbitrarily, then we can program this machine to a given Ising problem by just connecting those magnetic domains to each other. And you can expect that this physical system will have an energy that would represent the Ising energy of the problem that you programmed on the machine, which has the tendency to go to the lowest energy state. So it has the tendency to operate in the ground state. So that means that if you turn it on, it should converge to something close to the ground state. And you should be able to measure that. And that's how you can have a solution to the problem that you programmed on the machine. So we pick an element, a building block, to actually make such an Ising machine, which is based on degenerate optical parametric oscillator. And what it is that it's an optical resonator, which has a nonlinear element in this. And that's usually just a special type of crystal. But what happens in this nonlinear resonator is that you start with a pump. So you start with a pump frequency, a laser, and then you generate an output which is at half the frequency of the pump. And that's important because if you go through the math, you realize that whenever you turn such a system on, it either goes to a 0 phase or a pi phase. So there's a natural bifurcation that happens around the oscillation threshold, meaning that you turn it on, it either gives you 0 phase or pi phase. So you can use that to represent an Ising spin. So now the idea of using these OPOs to make an Ising machine is that now you know each of these OPOs can represent an Ising spin. If I can arbitrarily connect them to each other by just taking the field from one and just injecting it into another and do this for all the couplings that I want, so maybe I can map the problem of finding the ground state of Ising Hamiltonian to something in this physical system that the system has the tendency to solve it for me. And the mapping seems to actually work really well. And what happens is that the Ising Hamiltonian, or the problem of finding ground state, maps to this problem of what would be the phase states for each of these OPOs that would satisfy maximum number of couplings. Because each of those couplings are going to put a constraint on the phase. And then when the OPOs turn on and they pick up either 0 or pi, they're either going to satisfy the couplings between them or not. So the problem becomes, can this OPO satisfy the maximum number of coupling constraints? And the way it works is that when you turn the system on, there's no photon at the output. So you basically have quantum noise, whatever that is. So you start to building up your photons by just pumping it more and more. And these OPOs are going to start talking to each other to decide about how they can satisfy maximum number of coupling constraints. And then they're going to freeze into one of these phase states when they go above threshold. And you hope that this thing is close to the ground state of the problem you mapped on it, and then you can measure that, and you have an answer to that. So this is the idea of making a nonlinear optical-based computer, which is not a standard von Neumann architecture, and it's also specific about the Ising problem. So when we had the idea, we thought about doing some numerical simulations using just the simplest possible models we could use for each of these OPOs to just see that it does anything that looks like computation. And it looked like it did, so we went ahead to actually build a machine like that. So the building block in the actual machine is actually pulsed OPO, meaning that I start with pump pulses, which has a carrier frequency of pump omega pump, and then I generate pulses which has a carrier frequency of exactly half of this. And how it looks like is that it's a long resonator, so the light can go around this path, and it resonates in it with a nonlinear crystal, which in this case is how it looks like in the real life. But the key is that the round trip time of this resonator is exactly matched the repetition period of the pump. So one pulse goes one round trip, the next pulse comes exactly on top of that. So it's a synchronous pumping of this resonator. So we have been working on these for different applications, which I'm not going to talk about. But I'm going to tell you how we actually get the important property of these OPOs, which is the binary phase that we can use for representing an Ising spin. So to emphasize on that, I'm going to show you a mechanical analogy. In this video, I'm going to use two pendula. Each of those pendula is a parametric oscillator. It's a parametric oscillator, and in this video, I'm going to modulate a parameter of this pendulum, which is the length, by pressing on the string. And that modulation is going to lead to oscillation. So that's how it's a nonlinear system. And what you're going to see is that the frequency of pump, which is my hand, is twice the frequency of oscillation. And the oscillation starts with small amplitude, and then it gets amplified, and then they start oscillating. Each of them is oscillating in a different phase state. So it's either 0 or pi with respect to each other. So that's basically how things look like in the parametric oscillators at degeneracy. So in the early days, we did an exact experiment, but with optics. So we built two resonators, two of these nonlinear resonators. We pumped them with the same pump, and we tried to see if they actually show that phase state selection. The difference is that in the mechanical case, the oscillation starts from some mechanical vibration that exists in them. In the optical case, there is no photon at those wavelengths that we're talking about, so it starts from so-called vacuum fluctuation and quantum noise. So they pick one of these phase states, and we can see that in the experiment through the interference, purely based on quantum noise. So it's a quantum random process. So if you have an individual OPO, you turn it on, it's just based on quantum noise. It's going to pick up either 0 or pi. So now we want to use them and couple them to each other to actually solve an computational problem. So I want to tell you what kind of problem are these problems that we're trying to solve. And I'm going to give you this example of Maxcut, which is mostly all the problems that I'm going to show you in the actual experiments. So the Maxcut problem is a problem in graph theory, which is if you're given a graph, how can you split that into two subgraphs and you cut the maximum number of edges? And it's shown that this is an NP hard problem. And if you have this graph, which has 4 nodes and all the possible edges, If you split it through the middle, you're cutting 4 edges. So that's the maximum number of edges you can cut. But if you split 3 nodes on one side and 1 node on the other, you're only cutting 3 edges, so that's not a max cut. So this is basically how the problem looks like. So this maps to an OPO network problem by making 4 OPOs and just coupling them all out of phase. So out of phase means that I take the light from one OPO, I flip its phase, whatever that phase is, and I inject it into the other. And I do it for all these possible couplings. So I know that each time I turn these OPOs on, they're either going to be in 0 or pi. So if 2 of them are in pi and 2 of them are in 0, I know that this coupling, which is out of phase, is satisfied. These couplings are all satisfied. So we have 4 satisfied couplings, and that corresponds to cutting these 4 edges. And if 3 of them end up in 0, 1 in pi, that corresponds to only satisfying these 3 edges. So it's not the maximum number of satisfaction for these coupling constraints, so it's not a max cut. So that's basically how the max cut problem one-to-one maps to this OPO network problem. And this is one of the early experiments that we did. So how can we make 4 OPOs, couple them all together out of phase, and see if it actually computes this instance of NP-hard problem, or the max cut solution. So I'm just going to skip a lot of details, and I'm just going to talk about a magic technique that we used that later enabled us making really large machines. And that is called time division multiplexing. So you remember I said the round trip time in the resonator is 1 repetition period, so we always have 1 pulse in the cavity. In this case, we make the round trip time 4 times the repetition period, so we always have 4 pulses in the cavity. So you can think of this as 4 temporally separated OPOs in one resonator. And then what happens is that you can actually now make them interact with each other. So you can introduce those couplings between those OPOs by just introducing a slight output coupling and delayed by exactly 1 repetition period and injecting it back. So you take the field out, you wait until the next pulse comes in, and then you inject it on top. And you do that for all the integer factor of the repetition period. When you do that, you make 3 delay lines, and you make sure all those couplings are out of phase. Then you have a machine that represents that max cut problem that I talked about. So now the question is, can I measure the output? And the output measurement is simple. You can just look at the phase of the output of the OPOs. And the question is, how many times does it find the answer, and how many times it fails? So this was the first experiment, and we ran it 1,000 times, and we counted which phase states we see how many times. And it looks like that all the times that it turned on, it actually found one of the answers of the Maxcut problem. So 1 computer for 1 instance of an NP-hard problem, the smallest NP-hard problem, with 100% success rate. So it was a good starting point. But now the question is, how can we scale up and make a larger machine so that we can actually show computation with this? So the magic of time division multiplexing is that you can make the resonator long, so you can put as many pulses as you want, in principle, in that resonator. And if you make n-1 delay lines, and you can control those delay lines synchronously with your pump, you can actually create any arbitrary Ising problem on that machine. You can think of using optical fiber technologies and devices that we have available and implement such a hardware. And you can also think about using the evolving integrated photonic technologies that have the required nonlinearity in them. So these are the directions that we are taking. I'm going to just briefly talk about another idea that enabled us to make a large machine in a quick and dirty way. So let me tell you a little bit about that idea. So if you look at this network in the time division multiplexing scheme, so you have a long resonator with n pulses in it, and then you have a network of beam splitters and modulators. So the idea of measurement feedback is that, can we simulate what would have happened in this network of beam splitters on an FPGA and replicate what would have happened at the output of such a network and inject it back into the resonator? So of course, this is not equivalent to that optical interactions, and that's why it's a quick and dirty way of doing this. But it's so tempting because now you don't need to make all these optical systems. you can test if there is any meaningful computation with such a machine. So that's why we did this. And this is actually how the machine looks like. So it is a bunch of optics with an off-the-shelf FPGA, a long resonator. In this case, we had 160 pulses in the cavity. So we could use 100 of them, and we could implement any 100 to 100 kind of couplings between them. So we could implement a large number of Ising problems on the machine and see if this type of machine is actually doing any computation. So that enabled us to run several thousands of problems so that we can actually look at it now as a computer. So of course, I'm not going to show you a lot of the results. I'm just going to pick some and just tell you why they're interesting and promising. So this is one example of the graphs that we put on the machine, and we looked at how much time it takes to actually find an actual ground state of these problems that we put on as a function of graph size, so for all the way n equals 100. And the blue curve is what you should look at now, which is the actual time it takes for finding the ground state of the Maxcut, the Ising Hamiltonian. And as you see, there's no exponential speed up, so it scales exponentially, and as you expected. So as you increase the size of the graph, it gets slower and slower. But what is interesting in this experiment is that if you relax your requirement for finding the absolute ground state and you say you're satisfied with something within 6% of the actual ground state, then you get something like this red curve, which is flat as a function of graph size. So that means that it might be useful from many practical applications when you don't actually need the exact solution, but you want something quickly. So we're still continuing the benchmarking and trying to see if there is any way forward to actually use this as a better computer for these types of problems. But I'm going to show you another comparisons that we did, and that's with the DWave quantum annealer that is now commercially available. So apart from the differences in the physical properties, including the price, you can actually look at the computation performance of these machines. And this is for a special type of graphs that we actually implemented on both machines. And if you look at the results on the Ising machine, again, the graph size and then the time to solution, you see a similar curve. There's again the exponential decay, the exponential growth in the time to solution in the Ising machine. But if you look at the DWave machine, you see that it's exponential with n squared instead of exponential n. And the reason that that's the case is because in the optical implementation, we have possibility of all-to-all connection. So you can take any OPO and connect it to any other OPO, and that's one of the critical things in the time division multiplexing and optical implementation. But in the DWave machine, we're limited to this sparse connectivity of the hardware, which is implemented in the so-called chimera graph. So that means that if you have a dense graph and you want to implement it on 2,000 qubit machine, you actually need to use multiple hardware qubits to implement one node of the graph. And that usually scales by n squared. So you have the overhead in terms of how large of a graph you can actually implement, and that's why we couldn't go larger than 50, even though we had 2,000 qubits. And also the computational time scales as a number of exponentially by the number of actual hardware qubits, not the number of nodes in the graph. That's why you see an exponential n squared as opposed to exponential L. So just to plug numbers in, you see that this matters, even though there's nothing about the physical processes that is responsible for doing the computation. But we're just assuming that everything is going to stay exponential. But because of connectivity, you're going to pay a big price for the computational time. So this is one of the benefits of optics, and that's why optics provides some opportunities to actually implement these types of non-bound Neumann architectures. So what we have done so far is that we know the idea kind of works. There is computation at least, so it's not just giving us noise. There's something that looks like computation. We know we can make large machines. We can get the connectivity. So I'm going to just tell you what are we working on now and what does the future look like. So if you think about where we are now, and if you compare it with how computers, digital computers have evolved in the past 60, 70 years, you see that we have gone from like 1,800 vacuum tube digital computers to more than 7 billion transistors in the palm of your hand. So where we are now in terms of optical computing is probably very similar to what we had with the vacuum tubes. So it's a tabletop, large kind of setup, and it doesn't really allow you to make really large number of OPOs in the setup. So one of the directions that we're working on is how we can bring nanophotonics in and how we can get those types of architectures implemented on a chip. So the other direction that we're working on is that how we can utilize other physical mechanisms that are available in the optical domain that we can actually hopefully use for computation. So one of the things is about quantum behavior. So the pendulum that I showed you, which was either 0 or pi phase states, the question is, can we bring that into the optical domain and have the OPO operate in this quantum superposition of these 0 and pi phase states? And you do some calculation, and it looks like that in principle you can get there. And if you get there, you will access the regime that is already available to the superconducting qubits in terms of the quantum behaviors. And if you do that, then you can utilize the other opportunities that optics provides, most importantly, the connectivity and the scalability. And then you can make really large-scale computers that can probably benefit from the quantum nature or other types of physical processes in them. And that path also goes through making things on the chip and an integrated platform. So the other important thing is that we're, of course, not limited to Ising. The Ising was a simple case because the map was 1-to-1. And I told you at the beginning that Ising is special because it's NP-hard, so you can map anything else to the Ising. In principle, that's true, and that doesn't sound hard on the paper because it's only polynomial. In practice, polynomial means a lot. So n cubed, even though it's not exponential, it already means a lot. So the question is, can we have a way of mapping different types of problems onto the hardware in a more efficient way? And of course, can we utilize that to do more like quantum algorithms and quantum type computation with these types of platforms? So with that, I stop here and I thank you for your attention.
Any questions, folks have? Okay, can you get the mic, or somebody can pass the mic to
Hello. Thank you very much. I really enjoyed it. And I have a strange question. You showed a chip with a small tunnel underneath it. I felt it was a, and then you showed a resonance. Yeah, there. Now, when you do, my question is this: is you have there an optical bench, then you have a chip. Is there a difference, or has anybody ever tried that, to have a Raman beam to see if you have obtained some type of resonance? Use a Raman effect as opposed to get the type of.
So I think your question is about the type of nonlinearity, and you're asking about Raman nonlinearity.
Right. And to see if you see some type of connectivity between the two as you resonate there.
So in this case, we are trying to avoid Raman. So Raman is not the type of nonlinearity that helps us do the computation. Okay. So we're trying to make the other nonlinearity, which would give us the phase bifurcation and the 0 pi phase, stronger than Raman. But Raman usually exists everywhere.
Right.
So all we are trying to do is to make sure that the nonlinearity we care about is much stronger than Raman.
Oh, okay, good.
But yeah,
okay.
But Raman exists.
Thank you.
Sure.
Okay. Was there another one, or? Okay, I guess we can thank.
There was one.
Oh, sorry. Oh, yeah, right there. Okay, I was looking elsewhere.
Sounds like this technique would be very interesting for factory scheduling. Specifically, I'm familiar with doing it for semiconductor factories, and it's interesting problem.
That's right. Yes, I think the scheduling is one of the problems that people have mapped to NP-hard problems. And again, that falls into the other categories of not directly being the Ising problem, but there is a map. And if we can do the direct mapping to the hardware, I think that would be a polynomial beneficial thing to do.
I think those are NP complete.
That's right. So NP complete is a, well, depending on how you classify things, is a subclass of NP hard.
Okay, so thanks, Alireza again for a very interesting talk.